So we're going to be moving on to Dr. David talking on the topic of space solar power delivery for enabling environmental programs. Really quickly, Dr. David Dotson is a computational physicist with a background in macromolecular modeling and simulation. He has always been drawn to the space sector and is working to advance the cost to permanent high throughput space infrastructure. Aligning the people and resources to enable this mission is a personal professional driving force for him. David works as an independent consultant, specializing in bespoke systems and software engineering for ambitious science and engineering efforts. So it's our pleasure here at Blue Marble Week to welcome Dr. David Dotson.
Thank you for that introduction, Leo. I appreciate that. Okay, I'll go ahead and share my screen. Can everyone see that okay?
It's coming.
It looks great. Thank you, David.
Perfect, thank you. Yeah, so as Leo said, my name is David Dotson. My background is computational physics, in particular physics-based molecular modeling and simulation. I still actively work in that domain and I love that domain as an independent consultant. And I currently do a lot of work as part of the Open Force Field Initiative and recently started work on the Folding at Home network as well, which is the world's first exaflop computing system, if you've been following the news during the pandemic. I'm a relative newcomer to the space arena, but my interest in space elevators has persisted since I was a teenager. And I'm in a position now where I can actively work to execute on this vision that we've all long had. I intend to leverage my technical expertise and passion for ambitious projects to do my part in making space elevators a reality, delivering measurable value for humanity in the coming decades. But that's enough about me. In this century, global electricity demand is expected to roughly double from its 2014 value of about 2,400 gigawatts to over 4,700 by 2050. Now, China is a large driver of this growth, but India and much of the developing world is expected to increase its demand over the course of this time. The electrification of transportation in the US will also increase demand for electricity domestically, displacing the current use of fossil fuels for this purpose as well. But of course, this isn't the whole story. Addressing climate change is one of the major policy priorities for many countries this century. And to meet the commitments of the 2015 Paris Climate Agreement, many of the world's leading nations are aiming for net zero CO2 production by around 2050. Among these are Japan and China, having committed in the past year to 2050 and 2060, respectively, for that milestone. Other major fossil fuel consumers, such as South Korea, the EU, and the US, have declared similar intentions. And they're certainly looking to set a specific target for net zero. Now, all of this activity is intended to limit the global temperature increase to below 1.5 degrees C by 2100. Major CO2 emitters achieving carbon neutrality, followed by carbon negativity, is necessary for a 1.5 degrees Celsius trajectory to be possible, shown here in green. To achieve this, vast increases in renewable electricity sources will be required. Now, we believe that space-based solar power can be part of the solution to both of these problems. For those unfamiliar, space-based solar power, or SSP, is an idea that has been around for about half a century, first proposed by Peter Glaser in 1968. This entails a satellite, often positioned in a geosynchronous orbit, featuring mirrors and a photovoltaic array for collecting solar radiation in space, a microwave or possibly laser transmitter module directed at Earth's surface, and a ground station with a receiver, such as a rectifying antenna, that can convert the received beam into electricity distributed via the local power grid. Now, such a system features many advantages compared to a terrestrial solar farm. We get consistent high output, largely independent of latitude. The system is not subject to day-night cycles, reducing or eliminating the need for battery storage at the ground station. In other words, it's almost always noon at GEO. A microwave beam is generally unaffected by local weather or cloud cover. And we get greater land usage efficiency compared to terrestrial solar. So with all of that, you might ask, with all these advantages, what is the problem? Well, Peter hit on this. The problem is that mass to orbit remains a major barrier. For a system like the SPS Alpha Mark II, illustrated here, to deliver 2 gigawatts of continuous power to a 28.3 square kilometer ground receiver at 2.45 gigahertz with a 2.45 gigahertz microwave beam. With these characteristics, this requires a whopping 10,000 tons in orbit at GEO, or 36,000 kilometers in altitude. So to say it again, for a 2 gigawatt system, we need 10,000 tons delivered to GEO. And to put this into perspective, this is on the same scale as the total payload humans have delivered into orbit and beyond to date, measured in the tens of thousands of tons. I should say that despite this, we're actually confident that with the launch schedules being pursued by Mr. Musk at SpaceX and Mr. Bezos at Blue Origin, deployment of such a system could be possible in the next decade. And there's a real opportunity here. If we take the 5 largest US cities, we can ask the question, how many SPS Alpha Mark IIs, for example, would it take to provide for their average electricity needs today? For today's needs, we could meet New York City's entire average electricity needs with a trio of SPS Alpha Mark IIs. We could meet Houston or LA's needs with a pair of them, and Chicago or Phoenix with about a single system. Now again, these are for today's requirements, and they aren't factoring in the requirements for peak load, but it does give a sense of the scale. It wouldn't take too many such systems to provide electrical power for an entire large city. Now, I said earlier that we're actually pretty confident that deploying SSP by rocket is possible. I'll make that clearer here. In this table, we have a selection of launch vehicles from SpaceX and Blue Origin with max cargo mass values for putting the payload into a geosynchronous transfer orbit. So this is not low Earth orbit delivery. Now for the SpaceX Starship and Blue Origin New Glenn, these are our best guesses from material published so far. But the takeaway here is that thinking in terms of a reusable 20-ton to GEO launch vehicle is a useful exercise for assessing feasibility. Launch of a single SPS Alpha Mark II requires 500 launches with such a vehicle, even the 10,000 ton requirement. Now, as we just saw, we need about 3 systems to cover New York City today. This would be about 1,500 launches. And we think this will be feasible by 2030 to 2040. Elon Musk of SpaceX has stated his goal of 3 launches a day to support his Mars colonization effort, or about 1,000 a year. And that kind of scale for an SSP deployment program would work for meeting the needs of New York City. This is on the order of magnitude of what you need. But what about scaling out to the needs of the whole country? Satisfying 1/8 of today's electrical demand in the US would require 30 SPS Alpha Mark IIs. And now you can do the math. This is 15,000 20-ton to GEO launches. On a schedule like Musk is aiming for, this is 15 years of continuous launches, again, to meet 1/8 of today's US demand, today's demand. We zoom out even further. If we want to satisfy 1/8 of today's global electricity demand, this would require 150 such systems. This is 75,000 of those 20-ton to GEO launches, or about 75 years of 3 launches a day for this kind of launch vehicle devoted to this program. This is too long to be part of the global climate change strategy in this century. It turns out that to meet 1/8 of global electricity needs with SSP by 2100, if you wanted to do this with rockets or a 20-ton launch vehicle, an average of 3,500 launches a year would be needed, starting in 2030 and extending to 2100. This is a 30x increase from annual launches today, globally, very few of which are heavy launch vehicles capable of 20 tons to GEO. Now, I want to lighten the mood a bit. This isn't a talk about what we can't do, however. I'm going to argue that if you want to deploy SSP at scales meaningful for a global climate change mitigation strategy in the 21st century, you really need space elevators. Now, this table gives the space elevator development program proposed by ISAC. It begins in 2037 with the first such elevator up and running in an initial operating capacity, or what we call IOC. An elevator like this is proposed to have a transport throughput of 14 tons per day. And we have columns on the right giving the maximum mass deliverable in a year, as well as the accumulation of this number over each year of operation. Now, shortly after having a first elevator, we anticipate having a second, probably at the same site the following year. And the ISAC program proposes 6 elevators in total by 2041, followed by a conversion of these elevators to full operating capacity starting in 2047. Now, each full operating capacity, or FOC elevator, is proposed to have a transport throughput of 79 tons per day. What this gives us is by 2051, all elevators would be operating at full capacity under this program for an annual throughput of 173,000 tons for the whole set of systems. Now, this development program could enable deployment of SPS Alpha Mark II at large scale. If full scheduled capacity were allocated to this effort, 4 such systems could be deployed at GEO by 2040. By 2050, we would have 56 SPS Alpha Mark II systems at GEO. And at full operating capacity for all 6 elevators, the total throughput could deliver up to 17 systems into orbit a year. Now, this is a remarkable set of statements, and recall from the discussion earlier that each SPS Alpha Mark II would require 500 heavy launches to GEO. The throughput of these 6 elevators in 2051 to GEO is the freight equivalent of 8,500 heavy launches a year. So where does this leave us? If we take as our mission deployment of SPS Alpha Mark IIs at GEO to deliver 1/8 of the world's electricity demand in this century, can we actually do it? Well, we'll return to our first figure. This is giving rising electricity demand, both historically and projected, to 2050. We can use this projection as our starting point for modeling forward in time to 2100, and we've done so here. The solid green, orange, and blue lines on the left give the projection model from the US Energy Information Administration that was displayed as the dotted line in the previous chart, divided by 4, 8, and 16 respectively. So this gives demand 1/4 of the global demand, 1/8, and 1/16 of global demand. We observe that this model is relatively linear over its domain from 2030 to 2050, and so we can likely get away with modeling it with a least squares linear regression and extrapolate forward to 2100. Now, this may not necessarily reflect the reality beyond 2050. It's hard to make these kind of projections, but it is a starting point for analysis given the shape of the projection before it. And now we can take our discussion on heavy lift rocket launches from earlier and ask, assuming 3 launches a day, that is 1,095 launches a year, devoted to SPS Alpha Mark II deployment, starting in 2030, how much power could be delivered by SSP over time? We show this as the red line here. As we noted in that discussion, it would take about 75 years of launches at this rate to meet 1/8 of current global demand. But we see here that the rate of demand growth for that 1/8 line in orange actually outpaces the rate of deployment. A far greater average rate of 3,500 launches a year would actually be needed to meet this orange line at 2100 if you were starting to do these kind of launches at 2030. But what about the ISAC Space Elevator Development Program? If we had the full throughput of the program allocated to SPS deployment, what we get is the violet trajectory. Note that the slope of this trajectory is constant after 2051, where the ISAC development program ends at 6 full operating capacity elevators. And the throughput of this program would be enough to deliver 1/16 of global demand by 2056 and 1/8 of global demand by 2068, or 728 gigawatts and 3.6 million tons of hardware at GEO. What's more, by 2100, this set of systems would have delivered up to 9.2 million tons to GEO and beyond, a total of 1,842 gigawatts if all of that hardware was composed entirely of SPS Alpha Mark IIs. This is nearly 1/4 of global electricity demand by 2100. Now, this analysis is rather simplistic, but the conclusions are robust given the wide gap we see between what is proposed for launch rates by industry leaders and what would be needed to deliver SSP at scale. Even though it appears unlikely that an SPS program deployed via rocket would be capped at 3 launches a day for 70 years, it is also unlikely that space elevator construction and advancement would stop in 2051 if the ISAC program is successful. The gulf in throughput for hardware delivery between these 2 systems is too stark to ignore. This isn't intended as a castigation of rockets, despite what it may sound like. What we propose is actually a dual space access architecture for the 21st century and beyond, utilizing both rockets and space elevators, leveraging their strengths. As we saw, it's possible, and we believe actually likely, that rockets will deploy the first SPS systems. Rockets are incredible Earth-to-orbit systems for deploying new space technologies and opening up entirely new activities. They will also remain the go-to technology for putting humans into space, in particular, moving them quickly through the Van Allen radiation belt. But space elevators are needed for high-throughput, massive hardware deployment. They give consistent, continuous movement of freight to GEO and beyond. and they truly enable space technology deployment, such as SSP, at a scale needed for high impact. Not single systems, but hundreds of systems. The core message is rockets and space elevators are complementary technologies for enabling humanity's expansion into space. And the time for a concerted, funded space elevator development program is now if we hope to leverage their strengths in this century. Thank you for your attention. Are there any questions for me?
Great talk, David. That's a good summary of where the space elevator can enable environmental health of the planet, which is one of the missions. Massive movement of equipment. Okay, any other questions?
David, can you confirm, a lot of numbers there, so I just wanted to make sure that I was correctly understanding what you said. You were saying 1,095 launches per year would take 75 years to get to a certain level of capacity?
Yes.
Okay. That's with only a single Starship, right?
So that's with, how do you mean only a single Starship?
Well, the numbers that you're quoting are the same numbers that I operate off of Elon Musk. It's 1,095 maximal launches per Starship per year.
That's 1,095 launches a year. Elon Musk is aiming for 3 launches a day.
Right, 3 launches a day per vehicle, right?
I don't think that's his quoted number at all.
Of course, 3 launches a day is for a specific Starship from a specific facility. So if you have a fleet of 100 Starships, they could all operate 3 times a day, and that was based on return time for geo in orbit and all that kind of stuff. So it's definitely a maximal, but the numbers that I use is 1,000 launches per Starship per year at peak.
So that's contrary to my understanding of, and to be fair, Elon Musk has shared some of this just via tweet, so it's not necessarily easy to pull up the nuance.
He was just winging it, right? So he basically said, let's say you got a 4 to 6 hour turnaround time, right? That's where the number came from, 3 launches a day, based on the assumption that you had to do a certain amount of turnaround time in refurbishment.
I don't think you're going to have a vehicle prepped and ready to launch quite that quickly. Now, I'm willing to be surprised by Mr. Musk because he tends to do what he sets his mind to. I don't know that I've understood his statement as meaning that. That seems a bit aggressive.
I would suggest we don't argue the numbers that Mr. Musk did. David said 1,000 launches a year, period. If you want to launch a third of that by having 3 launches a day by a single vehicle, who cares? The point is that it's 1,000 launches per day. I mean, per year.
And the point I really like to make is that even if you scale this number up substantially, it doesn't change the conclusion. So you would require 3,500 20-ton to geo launches a year, starting in 2030, all the way to 2100, devoted to this program to reach this point, if you can see my mouse.
Understood. I guess my counterpoint, and where Peter's going, who cares, is that we're looking at literally ordering 100 Starships for a purpose like you have as part of the program, so that, you know, if you wanted to get it done in a shorter timeline, you can throw more ships at it.
I hate to bring up a silly point because we don't want to downplay the value of rockets, okay? But we are addressing the value of space elevators. If you want to start discussing the value of rockets, you have to toss in some other factors, like the environmental impact of black carbon on the ozone hole for every launch. And that's been a constant in every environmental impact statement. But they always come to the same conclusion. If we only launch a few vehicles a year from every site, it will not be a significant issue. If you ramp up to the numbers that you're talking about, the impact must be assessed. I don't know what the impact is. Nobody has done that statement. Nobody has done that. But if we want to start talking about impact, let's talk about all the impacts, financial, environmental, and everything else. And so, Chris, I don't think it's a time to discuss that. We would love, by the way, we want to invite you to have discussions on how do we go forward. You've got some really good ideas. But, you know, today we're going to be talking about the benefits and beauty of space elevators. And so my suggestion is let's take this discussion offline.
Okay.
Happy to do that, Peter. Happy to do that.
I'll put my email in the chat for you.
Yeah, thank you so much to Dr. Dotson for the presentation.